So the discrete Fourier transform is, as you know, a very, very important algorithm in engineering and in mathematics everywhere. Fourier is just a key idea. And so I think it's just good to know about those. So circulant matrices are connected with the finite size matrices, matrices of size n. So our circulant matrices will be n by n. And you remember the special form. So this is a key point about these matrices, C, that they're defined by not n squared entries, only n. If you tell me just the first row of the matrix, and that's all you would tell MATLAB, say C0, C1, C2 to Cn minus 1, then for a circulant, that's all I need to know, because these diagonals are constant. This diagonal is constant C1 and then gets completed here. C2 diagonal comes to C2 and then gets completed cyclically here. So n numbers and not n squared. And that the reason I mention that, or a reason, is that's a big selling point when you go to applications, say machine learning, for images. So you remember the big picture of machine learning, deep learning, was that you had samples, a lot of samples, let's say n samples, maybe, and then each sample in this image part will be an image. So the thing is that an image is described by its pixels, and if I have 1,000 by 1,000 pixel, so that's a million pixels. The feature vector, the vector that's associated with one sample, is enormous. So I have n samples, but maybe well, if they're in color, that million suddenly becomes 3 million. So say 3 million features. So our vectors, our vector of the whole computation of deep learning works with are vectors with 3 million components. And that means that in the ordinary way, if we didn't do anything special, we would be multiplying those by matrices of size like 3 million times 3 million. We would be computing that many weights. That's like impossible. That's like, and we would be computing that for each layer in the deep network. So it would go up so 3 million by 3 million is just, we can't compute. We can't use gradient descent to optimize that many weights. So the point is that the matrices in deep learning are special, and they don't depend, they are like circulant matrices. They might not loop around. So the circulant matrices have this cyclic feature that makes the theory extremely nice. But, of course, in general, we have matrices, let's say T0, constant diagonals, and maybe a bunch of diagonals, and here, not necessarily symmetric, or they might be symmetric, but they're not cyclic. So what are these matrices called? Well, they have a bunch of names because they're so important. They're linear shift invariant, or linear time invariant, whatever is the right word in your context. So they're convolutions. You could call it a convolution matrix. When you multiply by one of these matrices, I guess I'm going to call it T, you're doing a convolution. And I'll better write down the formula for a convolution. You're not doing a cyclic convolution unless the matrix cycles round. This would, when you multiply by C, this would give you a cyclic convolution. Say if I multiply C by some vector V, the result is the cyclic convolution of the C vector with the V vector. So big C is a matrix, but it's completely defined by its first row or first column. So it's really, I just have a vector operation there. And it's a cyclic one. And over here, T times a vector V will be the convolution of a T vector with V, but not cyclic. And probably these are the ones that would actually come into machine learning. Linear shift invariant, linear time invariant. I would call it, so math people would call it a tuplets matrix. So that's why I used the letter T. In engineering, it would be a filter, or a convolution, or a constant diagonal matrix. These come up at all sorts of places, and they come up in machine learning and with image processing. But basically because what you're doing at one point in an image is pretty much what you're going to do at the other points. You're not going to figure out special weights for each little pixel in the image. You're going to take, if you have an image, say you have an image with zillions of pixels. Well, you might want to cut down, I mean, it would be very sensible to do some max pooling, some pooling operation to make it smaller. So that's really like, okay, we don't want this larger system. Let's just reduce it. So max pooling, that operation would be, say, take them 3 at a time, so 9 pixels, and replace that 9 pixels by 1 pixel, the max of those 9 numbers. That would be a very simple operation that just reduces the dimension. That's make it smaller, reduce the dimension. Okay, so that's a cheap way to make an image 4 times or 9 times or 64 times smaller. But the convolution part now, so that's not involving convolution. That's a different operation here. Not even linear. If I take the max in each box, that's not a linear operation. So, but it's a fast one. Okay, so now where do circulants or convolution or tuplets matrices or filters come into it? So I'll forget about the max pooling. Suppose that's happened and I still have a very big system with n squared pixels, n squared features for each sample. So I want to operate on that by matrices as usual. I want to choose the weights to bring out the important points. So the whole idea is on an image like that, I'll use a convolution. I'll use the same operation is happening at each point. So forget the max part. Let me erase, if I can find an eraser here. Okay, so I'm I'm not going to, we've done this, so that's done. Now I want to multiply it by weight, so that's already done. Okay. So what am I looking to do? What kind of a job would a filter do? A low-pass filter would kill or nearly kill the high frequencies, the noise. So if I wanted to get a simpler image there, I would use a low-pass filter, which might just, it might be this filter here with, let me just put in some numbers that would say a half and a half. So I'm averaging each pixel with its neighbor just to take out some of the high frequencies. The low frequencies, a constant image, all black image would come out not changed. But a very highly speckled image would get largely removed by that averaging. So it's the same idea that comes up in all of signal processing filtering. So just to complete this thought of why do neural nets, so I'm answering this question. How do they come in machine learning? So they come when the samples are images, and then it's natural to use a constant diagonal matrix, a shift invariant matrix, and not an arbitrary matrix. So we only have to compute n weights and not n squared. Yeah, so that's the point. So that's one reason for talking about convolution and circulant matrices in this course. I guess I feel another reason is that everything to do with the DFT, with Fourier and Fourier transforms and Fourier matrices, that's just like stuff you got to know. I mean, that's every time you have you're dealing with vectors that are sort of where shifting the vectors comes into it, that's Fourier is going to come in. So it's just we should see Fourier. Okay. So now I'll go back to this especially nice case where the matrix loops around, where I have this cyclic convolution. So this would be cyclic because of the looping around.